All right, silly people. Here's the situation. We have a spring, or it's a system with two masses connected uh, in a line with three springs, which I've labeled S1, S2, and S3. The springs all have the same equilibrium length, A, um, uh, but the first and the third one have the same spring constant, K. The middle one has spring constant 3K. Um, and we're supposed to find the eigenfrequencies for the system and also the normal modes for the system. Um, Whenever you hear the word eigenfrequencies, you know that you're going to be solving this equation, the potential matrix minus omega squared times the kinetic energy matrix is equal to 0. Um, and when you're solving for normal modes, the equation that you want to use is eta I is equal to aij zeta j, where zeta is going to end up being the normal modes. Um, so we can just invert that to find eta j equal to 1 over aij uh, eta I, where aij are the elements of the eigenvectors that correspond to the eigenfrequencies for the system. Um, so let's get to it. We have to find what the potential tensor is. We know that it's just the Jacobian of the total potential of the system, eta I, eta j. There. So the way that I've defined variables means that this is going to be equal to del squared del x1 I del x2 or del xj, which will end up looking a bit nicer. So um, three spring potentials. For the first one, it's just k over 2 um, eta 1 minus the equilibrium position squared. Um, so Hooke's law potential, um, which I'm going to plug in my definition for eta 1 x1 plus a minus a squared. So it's k over 2 x1 squared. The third spring is very similar. It's just k over 2 eta 1 minus 2a squared. It's supposed to be eta 2, which is k over 2 x2 plus 2a minus 2a squared, which is k over 2 x2 squared. Nothing too crazy there. The middle one with spring constant 3k over 2, we're going to have this be, it's going to be the difference between the etas minus the difference between the equilibrium positions. Okay, so that's being 3k over 2 x2 plus 2a minus x1 minus a plus, or minus 2a plus a. So again, all of the equilibrium terms cancel out, so we'll just have 3k, that's supposed to be squared, 3k over 2 x2 minus x1 squared, for a total potential of k over 2 will have x1 squared plus x2 squared plus 3x2 minus x1 squared. We can simplify that. So I'm just going to expand the difference term in the middle. So it's going to be 3x2 squared plus 3x1 squared minus 6x2 x1, which means we really have 4x1 squared plus 4x2 squared minus 6x2 x1, which we can factor that 1/2 through to get this stuff here. Cool. Uh, so let's start taking partial derivatives. So del v del x1 will end up being 4k x1 ah 4k x1 minus 3x2 k. All right. Um, and then if we take the second derivative of that with respect to x1, we'll just have 4k. Let's now do x2, which will be 4k x2 minus 3x1. If we take the second derivative of that with respect to x2, we'll just have 4k again. And if we want to do cross terms, so del squared v del x1 x2, in this case they end up being symmetrical. So we have minus 3k and then del squared v del x2 del x1 also minus 3k. It's supposed to be a k there. Okay, so we can set up our potential energy tensor as 4k minus 3k minus 3k 4k. I don't know why I'm not doing a template on this right now. I should do that so that we can have lines. Yeah, that looks a lot nicer. Okay, we have the potential energy tensor. The kinetic energy tensor, as usual, is just the masses times the identity tensor. So m del ij. Both of the masses have the same mass m, so no worries there. So then this minus is just m omega squared del ij, the identity tensor, which we can write as it'll be 4k minus m omega squared minus 3k minus 3k gross. And then another 4k minus m omega squared is equal to 0. To find the eigenfrequencies, we just need to solve this equation. So we'll have 4k minus m omega squared minus 9k squared equals 0. Expand this squared term, we'll have 16k squared minus or plus m squared omega fourth minus 8km omega squared minus 9k squared equals 0. Let's reduce it a bit. So 16 minus 9 is 7. 7k squared plus m squared omega fourth minus 8km omega squared equals 0. This polynomial is actually pretty easy to factor. It ends up being 7k minus m omega squared there, and then k minus m omega squared there equals 0, which means it's really easy to solve for the eigenfrequencies. We'll have, if we set 7k minus m omega squared equals to 0, then omega is the square root of 7k over m. We're going to call that our first eigenfrequency, omega 1. Then if we also set k minus m omega squared equals 0, then omega, we're going to call omega 2, is just the square root of k over m, which is a frequency that we've seen before, to say the least. Um, all right, we still have to find the normal modes, which means we have to find the eigenvectors which correspond to these eigenfrequencies. To do that, we just set up the characteristic matrix again. We'll have it's 4k minus, what was it, m omega squared. That's going to be m omega j squared, and then we have minus 3k, 4k minus m omega j squared, times some eigenvector, which I'm going to call a1j, a2j, is equal to 0. Right, so when you do a little bit of matrix multiplication, you will see that you have 4k minus m omega j squared, a1j minus 3k a2j is equal to 0, and minus 3k a1j plus 4k minus m omega j squared a2j is equal to 0. So what you're going to find from these equations is that there's a free variable for each choice of j, um, which is fine, but that just means we'll be able to choose the simplest form of a1 and a2 that we can. What do I mean by that? So let's plug in a j. So let's do j equals 1 first. When we do that, we'll have 4k minus m times 7k over m. Yeah. Times a1j minus 3. Now it's j equals 1, so a11 minus 3k a21 equals 0. Simplify that, so it'll be minus 3k a11 minus 3k a21. What you're finding is that a11 is equal to minus a21 for this eigenvector, and then when you plug that into the other equation for the eigenvector, you'll just find that one of the variables is free. So let's have a11 just be equal to 1 and a21 equals minus 1, so that the eigenvector a1 will be 1 minus 1 divided by some normalization which depends on the mass. Cool. Let's look at j equals 2 then. Again, starting from the first equation, we'll just have 4k minus m times k over m, a12 minus 3k a22 equal to 0. This time we're going to have 3k a12 gross. 3k a12 minus 3ka22 equals 0, which you're just going to find that a12 is equal to a22, which means our second eigenvector, a2, is now 1 over m root 2 1, 1, choosing the simplest form. All right, that's pretty awesome. Let's look at the normal modes now, which it's this equation here. Da, 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 da. Cool. So writing this out, we'll choose j equals 1 first. Zeta 1 is 1 over summing over the i's, a12 x1 plus 1 over a22. This is supposed to be 1, so 1 there, a2, 1 there, x2. Which we had those equal to 1 over m root 2 times 1 and negative 1 respectively. So we'll have positive m root 2 x1 plus or minus m over m root 2 x2. What does that correspond to physically? That corresponds to the springs, the masses on the springs moving in different directions in a normal mode of oscillation. So they're literally moving like this with frequency 7k over m. The second normal mode, zeta 2, will be a1 2 x1 plus 1 over a2 2 x2, which ended up being equal to each other. So looks like that. What does that correspond to physically? It means that the springs are moving together in the same direction like this, with a frequency root k over m. All right.